Okay, shall we resume? So today we'll use GeoDa again. One more time. We have the notebooks. I think, I'm not sure if it's just a single notebook or if we have two for today's class. But anyway, they are already available to you. And we'll see then just using GeoDa now, but it's pretty much the same thing in the notebooks. We'll see the spatially constrained hierarchical clustering, the scatter, and then just one of the 5 different applications that we have available for REDCAP in GeoDa. Right, to do this, we'll follow the same example that Luke uses in the volume 2 of his GeoDa book. So we'll use the Ceará data. So the data set is about the Zika epidemic that we had in Brazil a few years ago. But the variables that we will use are not actually related to Zika. It's more about some development indices that we have for each of the municipalities in the state of Ceará. So we have the 184 municipalities here. And then here, as I said, we have all the data. We'll skip all these Zika and microcephaly primary care, like everything health related, and we'll concentrate on the mobility, environment, housing, sanitation, and infrastructure indices, and also the here, GDP per capita, the log of the GDP per capita for each of the municipalities. Okay, so let's begin with the spatially constrained hierarchical clustering. We can go straight to the clusters menu. You'll see that, of course, since we are now talking about spatially constrained methods, the weights matrix will be a required part of the implementation of these methods, but we can call the weights manager from within the option here for the spatially constrained hierarchical clustering. So I'll select the method here. And then in a pretty similar way for all the other clustering methods we saw for GeoDa, what we have is that the window is divided in dendrogram summary tabs, right, for the results. And here we have the parameters that we need to choose. So let's select these 6 variables that I just mentioned. So mobility, environment, housing, sanitation, and infrastructure, plus GDP per capita here at the bottom. Okay. So now the next step is to define the neighborhood structure, right? Because again, as we talked earlier, what the spatially constrained hierarchical clustering will do is that it will assess the dissimilarity for all these 6 variables, right? For each of our observations, each of the municipalities in the state of Ceará. But it will consider in the clustering procedure only the dissimilarities for municipalities that are neighbors of each other. Right? So if 2 municipalities, as we saw in the example earlier, in the Arizona County example, right? If 2 municipalities are very similar, but are not connected, are not neighbors of each other, that dissimilarity will not be considered for the optimization, right? So it will take into account just the intersection between the dissimilarities and the neighborhood structure, all right? So the way we do it, since we don't have any spatial weights matrix loaded yet, we can just click here to call the weights manager. Here it is. And now we can create a weights matrix. So select ID variable. We can do anything. We can use the code for the municipalities. Since we do have a contiguous state, so all the municipalities are contiguous to each other, we can use the contiguity matrix. So we'll use the queen contiguity and then just first order. So the most simple weights matrix are the most common. All right, so I'll hit create. I'll save it anywhere. I'll save it on my desktop. And that's it. So let me close this and this as well. So we can return to our clustering window. All right, so we have our 6 variables. We have the weights matrix. Now we need to choose the number of clusters. Remember, this is a hierarchical procedure. So the number of clusters that we choose here will not change the overall result that we get in the dendrogram, right? It will just change, sort of define where the dendrogram will be cut, and then we'll get all the statistics about each of the clusters, like the cluster centers, the within sum of squares, and all of that based on this number of clusters. So it doesn't really matter at this point how many clusters we set. So if you want, you can leave it at 2, or you can already do as Luke does in his book and choose 6. I mean, no, I think it's 12. We'll play with this anyway. Let me just get here my notes, because then I have the number. Yeah, it's 12. We'll have to standardize our variables, right? Because they are in different units, in different scales. And the method will use Ward's linkage because, again, it's the most commonly used approach. All right, so hit run. And here we have the dendrogram. So the dendrogram now, since I set the number of clusters to 12, the columns will be reflecting that. But if you did 2, doesn't matter, right? The only difference is that your bar will be here. No, one more. This is 3. Yeah, here, right? But then the overall result is still the same. So from this dendrogram, before we go to the summary, or even before we see the map, we can already try to identify what is the similarity that we have between the clusters and within each of the clusters as well. So as we talked about in our previous classes, the height in the dendrogram is showing exactly how much the similarity we need to take into account in order to allow for these units to be merged, right? So the greater the height where the merge occur, it means that the more different these units are. So then we can see, for example, that all these units here, that when we have 7 clusters, all these units that are part of this pinkish cluster here, they are very dissimilar from each other. So in the solution with 7 clusters, we probably have a very heterogeneous cluster here. But I mean, anyway, so it can help us choose how many clusters we want in the end. Okay, and also, of course, if we keep increasing the number of clusters, they become more and more, we have more and more singletons that will be created out of this result. All right, let's stay with 12, save and show map, so we can see exactly what we have from this. So now finally that number was used, the number of clusters, because again, being hierarchical, the advantage of the hierarchical clustering in comparison to the partition clusters, the partition clustering methods, is that we do not need to choose K beforehand, right? The number of clusters does not need to be chosen before we run the analysis. We can choose it after seeing the dendrogram and seeing the overall result. So this is a solution with 12 clusters. So what we get is the usual, as we talked about this, like several times this happens when we are using spatially constrained clusters. We get a lot of singletons. It's basically because we tend to have spatial outliers. So they are, of course, within the whole region, but they tend to show different values. And then they will be either in the agglomerative or the divisive approach, they'll tend to be picked out and end up as singletons. So in this solution with 12 clusters, we have 3 singletons. So we have this, and this, right? So these 3 regions, these 3 municipalities, they are the single members of their clusters. But not only we have singletons, but also we have clusters with very few observations, right? So from cluster 5 to cluster 12, so all these 8 clusters, they have at most 5 observations in each of them out of the 184. So again, unless we have a very heterogeneous region, a clustering result that is this unbalanced is usually not something that we would like to have. So it's something that we may need to change. But anyway, let's just keep this for now and evaluate the summary so we can have a better impression of what is the result that we got. So here from the summary, we get the cluster centers. So we can see the average of the indices and the GDP per capita for each of these clusters, right? So we can see the differences. So for some of the variables, the variation is like greater than for the others. But anyway, so from here we can classify or label the clusters if we were to end our analysis and stay with this result, then it would be an important step to be able to label these clusters. But let's not worry with this now. What we can tell just, by looking at it is that we have, for example, a cluster like this, cluster 6, which shows greater GDP per capita and like a small value for environment, also a small value for mobility, and that's what we would use if we were to label this cluster, right? We would need to take all these into consideration. Okay, the next thing we have is the total sum of squares. So that will be, of course, fixed for as many different number of clusters that we have. It's then the total dissimilarity that we have in our data. And here we have the within sum of squares, so we can see how is the homogeneity in each of our clusters. So from this, we know, of course, we can ignore the singletons that show 0. But from here, we can see that we have two clusters that show a sum of squares that is greater than 100. So again, usually these will be clusters that not only are more that have more heterogeneity, but sometimes since it's the sum of squares, it may be just that they have a lot more units in them, right? So you have these two things. But what is important to realize is that the variability that we have in the within cluster sum of squares is very high, right? So we have a lot of the homogeneity within the clusters is very different. And again, usually this is not something we would want to have. So one more point against this result. Okay, finally, what we have here is the ratio of between two total sum of squares. So this is showing us how well we were able to group those that are more similar and separate those that are more dissimilar. And we have a number here that is smaller than 0.5. We've been discussing this over and over in our previous classes. And a number that is smaller than 0.5 is usually not something, again, that is desirable. However, for spatially constrained applications, then we need to be more relaxed about this, right? Because the whole idea is that since we're adding a constraint, we cannot really expect the ratio of between two total sum of squares should be as high as something from the k-means or the k-medoids, right? They will tend to always be greater unless the result from the k-means and the k-medoids was already spatially constrained in itself, right, by the data itself. Then if we add the constraint and the constraint actually applies to these data, this tends to be worse. So we need to be more relaxed about this and take into consideration that we're weighing trade-offs here, right? So we are assuming, or at least we're imposing the constraint of spatial constraint, and by doing so, we get more intuitive or at least more geographically concise results, right? So they are more like a zoning or more like a regionalization. And the price we pay for this is less homogeneity, right? So the price we pay for this is a smaller ratio of between two total sum of squares, right? So that is the trade-off that we face when we're thinking about this. Okay, so if we think about what we have here in the hierarchical cluster map, what we can do just to check, we can right-click on it, and then we can go to connectivity and show graph. So this will plot the weights matrix on top of our result. Let me just change the color of this graph. So I'll go to connectivity again, right-clicking on it again. I'll change the edge color and I'll make it red so it's more visible. Yep. Of course, unless for the red cluster. But just to highlight what we have here is that, as you can see, elements or all units, all municipalities that are part of the same cluster, they are connected and they must be connected. That was the constraint for the optimization. Sometimes it may look like in this, may look like they are not connected, but they are, because the configuration that we chose, so the type of weights matrix that we chose was queen, and here we have at least one point connecting these different units, right? So they are connected, then they are part of, they can be part of the same cluster, even if they look spatially disconnected somehow. We have at least one dot connecting these cities, so these municipalities, so they get connected in the end. So it's not possible from this approach to have units that are in the same group and they are not connected. As we saw earlier, since this is a spatially constrained hierarchical clustering, for each of the steps in the iteration or each of the steps in the agglomerative process, right, when we were merging the municipalities, this weights structure was being updated. So, for example, let's just say that the first step was to merge these two units here, these two light green units. So if that was the case, for the following steps, even though this other municipality here to the north of the larger one, it is not a neighbor of the one at the bottom. But since these two, and we're considering that these two got merged in one of the first steps, what we have is that what will be considered in the end, let's see if I can select that. Yeah, no. Anyway, I'm not being able to select just these two. But yeah, so what we have is that in the end, what will be considered as neighborhood of this, the merged area, will be a union of the neighbors of the municipality that is more to the north and the municipality that is more to the south. Okay? So this is hierarchical constrained, spatially constrained hierarchical clustering. Let's not waste much time or much effort with this. We can just compare then what we got with the skater. Just one thing I think else that is important to show is that, let's say, for example, that we're not happy with this very large cluster with 79 observations. So we want to break it down, right? So the way the hierarchical clustering works is that for each step, right, the units are being merged and merged and merged. So if we want to break down this larger cluster, we need to roll back in the agglomerative process, right, and go to a stage where we had more clusters. So basically, we need to move the dendrogram bar until we see exactly at what point we can break that large cluster. Since it's a hierarchical process, what happens in one step gets propagated to all further steps, right? So everything that happens after. So what I'm saying is, if two units get merged, there's no way they'll be separated again. So the idea here is that if you want them to be separated, you need to go back into the hierarchical process and make sure that you stop in the step where they were merged, so you get them separated. So what we can see here is that if we wanted a region that was not as large as this one, we would need to have 22 clusters in our analysis for them to be separated, right? So that was the step when they got merged. So, I mean, it's a lot of complexity, right? To have out of 184 municipalities, you end up with 22 clusters. That doesn't sound very reasonable. So the bottom line here, I think, is that spatially constrained hierarchical clustering is not yielding good results for these data and these variables. All agree? Okay. All right. So let me close this. And then let's move forward and go to Skater so we can see what we get. So the menu clusters and now Skater. So again, let's select the variables. So 5 here, the 5 indices, plus GDP per capita. We can use the same spatial weights and also the same number of regions, so we can sort of compare. I don't remember exactly what was the BSS by TSS. I think it was 0.40 something, but we can run it again. And then everything else we can leave in their default values, so Euclidean and standardize, and I'll hit run. So for the scatter, even though the scatter is also a hierarchical approach, it is in the opposite way, right? It's a divisive approach. So all regions, all units, they start as a single cluster, and then we break them out until we get like as many clusters as we want. So we have the minimum spanning tree. We'll see it here. I'll just, we'll save it and see it like a few moments from now. But the whole idea is that everyone starts together and then we separate the regions like one at a time, right? Or in one group at a time in each of the steps. So it's a divisive approach. It's a hierarchical approach in the same way as the spatially constrained hierarchical clustering. But now for the scatter, we do need to define the number of regions beforehand. It doesn't change the overall result. We'll see that. So if we were to construct like a dendrogram for the scatter, it would be the same thing. It would be stable for all the number of possible number of clusters that we have. So what I'm saying is units that get separated in any step, they cannot be merged again. They will never be merged again, right? So it's a sequential process. But here we need to choose the number of regions beforehand because it's part of the way the edge that will be removed is chosen, right? It will, as I said, the algorithm will assess all the edges. It will find the one that has the greater cost. By that, meaning that it will find the one that by removing it, you have the greatest decrease in the overall dissimilarity of your data, and that will be removed. But then it needs to know where to stop to show us the result, right? So we can actually see what we have. So that's why in this case, we do need to define the number of regions before running it. So this is what we get. Again, before it was 3, right? Now we have 4 singletons, but still like a issue with singletons. The large region now has even more municipalities to it. Now we have 107 municipalities to the larger region. So there's still an issue here that we need to address. But before we work on this, let's just see what we get for the results, and then we can start trying to mitigate this problem. So, okay, clusters from 1 to 12, we have the centers here. Again, at some point, we'll have to label these clusters, but maybe not now. Within cluster sum of squares, now we can see the same issue, right? It's even worse that we have one cluster that has a WSS that is much different than the others. And the ratio of between two total sum of squares is 0.43, whereas in the spatially constrained hierarchical clustering, I think it was 0.44. So we got an even worse result, but pretty similar in terms of these, like the homogeneity, the final homogeneity that we have. But anyway, so it's still not very good, but let's see in the map what we can think more about the method and make sure we understand the intuition, what would happen behind the scenes for us to get this result. So one thing we can do in the scatter is in the output, we can save not only the cluster allocations, but also the spanning tree, right? So we can either save the spanning tree of this result, the result with 12 clusters, so after all the edges were removed, or we can save the full spanning tree, right? The complete spanning tree. Let's check this box and save the complete one, because this will allow us to actually identify exactly which edges were removed for the creation of the clusters. So after checking this, I'll save the spanning tree. And then I'll do scatter MST, save. And now the same thing we did before, once we did this, okay, sorry, this is important. Once we save the spanning tree, we are saving a new weights matrix, right? Because we're saving a new connectivity between our spatial units. If we go to the weights manager, let me try to find. Where's the GeoDa? Here it is, main menu. So if we go to the weights manager, you'll see that now a new weights was added. So now we also have the scalar MST. So if we want to see the connectivity that is created by or is represented by this matrix, we need to highlight it. So highlight the scalar MST. And then after we highlight it, so now it's the active weights matrix, we can go back to our result, right click, go to connectivity again, and show graph. Okay? So again, I'll just change the color. So connectivity, change edge color to red again. Slightly easier to see. So from here, we can see exactly what the scalar algorithm was working with, right? So for example, what we can tell is that, let me focus on this singleton here. So what we can tell is that from the MST, the only way for this municipality, the dark blue one, to be connected to this other municipality, and they are not actually not neighbors, but let's say this one then, to be connected to this municipality, and they are neighbors of each other. But since the minimum spanning tree is considering not only neighborhood, but also similarity in the abstract space of the variables, right? The way the Prim's algorithm works is that it's combining both things, both the neighborhood and the similarity of variables. So the only way for these two regions to be part of the same cluster would be if all the other regions connected them were also part of this cluster. Does it make sense? Right? Because they are not connected by the MST. So the MST, it started, the scalar actually, it started with that other map. Now it's showing only the active weights. It started with the queen weights, right? Where all the units sharing a border were connected to each other. But then it worked on that graph and made it into this open circuit graph where we have only one pathway between each of our observations based on the similarity of our units. And now we can see that this dark blue is connected only to this neighbor, to the one to the west, right? All the other neighbors are not connected to it. So the only way they would be in the same cluster is if all the others were also in the same cluster with them. Yes. Then yes, Julie. You can see from the MST, so the graph that we have now, shows you that only units that are neighbors of each other can be part of the same cluster, but not all units that are neighbors of each other can be in the same cluster. I think this is the main difference. Before, in the first method, all units that were neighbors of each other could be in the same cluster, right? Here, not all neighbors can be unless you have someone in between connecting them. Because the weights, the original weights matrix, it got transformed into this MST. So the spatially constrained is still clear here, right? Because these units, they can, like, you can never have that this green unit, like this municipality, will be in the same cluster as, let's say, this one, unless you have neighbors connecting them as part of the same cluster. So the spatial constraint is still explicitly applied. It is only in an even more constrained way, because now we don't have that the neighborhood and the weights matrix to be updated in each step and incorporating more neighbors. It's quite the contrary. You have very few possible ways, possible connections. You have very much fewer edges. You have only n-1 edges now connecting your units. So the intersection between the similarity in the variables and the neighborhood structure is what created this MST. And therefore, the spatial constraint is even, I would say, even harder for this method in that sense, right? Because not only you have to be neighbor to be considered for the same cluster, but you have to be a similar neighbor. And that those are the only ones that remain connected. Does it make sense? So you can see that it's still explicit, right? The spatial constraint in the graph. You only connect units that are neighbors of each other, but now no longer all neighbors are connected, only those that are similar. Okay, Michelangelo. Oh, it was the same? Okay, so yeah, I would say that in that sense, now the solution is even more constrained in that sense, because now you have that the neighborhood, it's, yeah, the connections are comprised not, or are based not only in the neighborhood, but in the neighborhood plus the similarity. So you have these two dimensions taken into account here. And by looking at this graph, we can identify, I mean, we cannot see from the graph exactly which regions were divided first, but at least you can see which edges were removed in the end, right? So if we have 12 regions as a final result here, it means that we removed 11 edges from our minimum spanning tree. So from this graph, 11 edges were removed. And it's quite easy for us to identify which ones, right? Because, for example, since this is a singleton, of course, it has only, like there is only one, like it had only one neighbor in the MST. And then since it had only one neighbor in this MST, that edge was removed and it became like an island, right? So this is one of the edges that got removed. So for the singleton, it's even easier to identify. But let's get this red cluster. No, the red is bad because I have a red graph. Let's get the dark green cluster. So in this dark green cluster, when we click on it here, on the category display here, it will select all the units, right? That are all the 3 units that are part of this dark green, this cluster 8. And then we can see that there is only one connection again. And so the edge connecting this unit to this one is the edge that was removed. And therefore, this 3 different units became one cluster among themselves. Okay? So why would you do this? What would be like the advantage of being able to identify this? Pretty much none, right? The whole idea is to understand what happened, but also to think that if I wanted this municipality or that municipality or that to be part of larger clusters, this will not happen, right? Because they were divided quite at the beginning and they will never get merged again. In the partition clusters, you can have that units that were separated for, let's say, 3 or 4 clusters. And if you increase the number of clusters, they can be merged again, right? Because it's all about the optimum for that number of clusters. But here, that won't happen. Once the edge is removed, you will assess only within the 2 sub-branches that you created. And then within those sub-branches, you will assess the sum of square deviations for each of them and choose a new edge to remove in the following step. Okay? So by doing this, what we think is, again, like if we see this large area and it's, this is like too large, I want it to be split, you need to increase the number of clusters in order to, luckily, or if you're lucky, one of the next steps will already be one of these edges, and then you will break this tree, this branch in 2. Okay? All right, but then of course, again, the price that we need to pay for this, if we want to break this larger area, is that we would have to have more clusters and then more complexity. And then the whole idea of running a cluster analysis may be lost, right, in this, because then we won't be simplifying much or decreasing much of the dimensionality that we have in our data. So one thing we can do with Skater is this, like the MST, it doesn't change, right? It's always this because it's based on the weights matrix that we chose and the variables that we chose as well, right? So the MST will always be this for the Skater, unless we change the weights or, again, we change the variables. But one thing we can do is, since the algorithm will go over each of the edges that we have, each of the 183 edges, what we can tell the algorithm, what we can do is add more constraints to this analysis. So again, if we're adding more constraints, it means we'll get worse results in terms of homogeneity, but they may be better in terms of interpretability or, for our research. So, I mean, again, the cost may be worth it. So what we can do is, let's say, for example, when the algorithm is checking this edge, right? Let me zoom in again. So when the algorithm is checking this edge, and in this result, it evaluated this edge and said, okay, it evaluated this edge and said, okay, this edge has a high cost. So by removing it, I decrease a lot the overall variability that I have in the data. So the overall sum of square deviations. So by removing it, I gain a lot. So that's what it did. But what we can do is add a constraint to the algorithm and say, once you evaluate this edge and you realize that by removing it, you end up with a cluster that has only one observation, just don't do it. Just keep moving. So this is one constraint we can add. And that constraint is represented by the minimum size of the regions that we may set. So what the algorithm will do is, let's say we say that the minimum size of the region is 10 regions. So once we check the full graph, the algorithm will check each of the edges and say, okay, if I remove this edge, I end up with a region that has a cluster that has only one unit, so not good. If I remove this edge, likewise, if I remove this edge, I have a region with only 2 units, so not good. And then it will just keep moving further until it finds edges that by removing them, we'll get 2 clusters of more than 10 units. And for those edges, it will check the cost and assess whether it's worth removing or not. Does it make sense? So this is the way the minimum size works, minimum region size. So, I mean, we can check it. Of course, if we do 12 clusters and let's say we do 10 minimum region size, we'll be having like a hard time, right, for the result because we have only 184 cities. And then if we do 12 regions of at least 10 elements, that is already 120, right? So we're reaching the limits. So maybe it would be better if we decrease the number of regions to only 6, right? So we give more flexibility to the algorithm. And I'll run. And see, now we get a result that is much more balanced. Is it great? No, right? We still have maybe a large region, but it's not that unbalanced anymore. We have 2 clusters that reach exactly the minimum size that we set. So basically, the constraint is being applied to them, not to the others. Or, of course, the results of the others will also be a result of the constraint, but at least they are not on the edge of the limit that we set. And if we see what we got for the results, we can see that the ratio of between to total sum of squares decreased a lot. Again, one more constraint, less homogeneity within the groups. But at least the result is becoming more and more easier to interpret in terms of a regionalization, or at least looking more like a regionalization. And then depending on our application, this may be what we want. So for the paper that we saw earlier today, right, the whole idea of creating regions for evaluating the hotspots of the coronavirus risk, being able to create spatially concise regions was really important, right? So it may be that for the application, this is the same. Okay, so this is minimum region size. So it's the simplest, like it's a very simple constraint. It's just that, like when the algorithm evaluates the edges, it will just keep moving if that edge results in regions that are smaller than that size. And the same thing can be done, not directly in the minimum number of minimum region size, but in the, like we can set a minimum bound to the clusters. So for the minimum bound, what we'll be choosing or what we'll be selecting is not a minimal size for the cluster, but a minimal sum of any variable that we choose in our data. So for example, we could choose a minimal bound for population. So we need to find the population variable here. Here it is. And then we can say that we want the clusters to contain at least 10% of the total population that we have in the state of Ceará, right? So now we're not saying that the clusters have to have more than like 1, 2, or 3 municipalities. If we have that one city here has more than 10%, it could be a singleton, right? So we not guarantee that we will not end up with singletons by doing so. But again, depending on the application, having singletons is fine as long as they are really outliers. So it really depends on what you're doing. So let's just do population here. Let's keep the 10%. Yeah, and let's just click run. And now this is what we get. So see, we have a region that has only 7 municipalities, and it's around the capital Fortaleza, right? So probably has some similarity with the metropolitan area of Fortaleza. But for all other regions, we have, again, quite some balance between the number of observations in each of them. And if we see the ratio of between two total sum of squares and compare at least to the other result, I mean, we moved from 0.21 to 0.22. So basically, we did not move anywhere. We're still in the same place. But again, it's a way for us to compare the results. Okay? Any questions? So as you can see, the scalar provides us with more flexibility to bring the whole art idea to the clustering, right? Because then we can play with the result. And as long as we're willing to pay the cost in terms of homogeneity, so having less homogeneity in our clusters, we can shape these regionalizations in a way that may be more intuitive or may be more aligned with the objective of our research, depending on what we need to do. All right. Okay, so let's move ahead and finally see the REDCAP. And as I mentioned earlier in class, the REDCAP is sort of a combination of 2 approaches in the sense that it combines both the agglomerative hierarchical approach with the divisive the agglomerative hierarchical approach of the spatially constrained hierarchical clustering with the divisive approach of the scalar. So let's choose again the same 6 variables. Now we need to make sure that the spatial weights are the actual full weights, right? The queen matrix, which I called here just Ceará Zika, but anyway, should have called queen, first order queen or something. For number of regions, since we want to compare, let's just start with 12. And the default method is full order word linkage, right? So the whole idea of the full order is that the dendrogram will be used to create the MST, like a dendrogram will be used to create the MST. So in a similar way, like the dendrogram that we have from the spatially constrained hierarchical clustering. But once the MST is created based on that dendrogram, the algorithm will work in a similar way as the scalar, right? In terms of the way the divisive approach will work. So let's do full order, word linkage, no minimum bound, no minimum region size. I mean, everything is fine. Let's hit run. So again, the same issues just repeat over and over, right? With the singletons, probably because That's what we have in this data, some heterogeneity in those municipalities. The ratio of between to total sum of squares is back to the order of 0.4, 40 something. If we start playing with minimum region size or minimum bound, it will probably again decrease to 0 to the order of the 20s in the same way. But yeah, that is the idea. What we can check, just so we can compare, is again, we can save the complete spanning tree. So I'll check the box to save the complete one and not the one with the 12, like the 11 edges removed. I'll call it REDCAP MST. Let me make sure that it's the one that is active now from the weights manager. And now we can show the connectivity graph. Let me change the color again. Red. And here it is. Okay, so let's see if there is, if I change here. Yeah. So as you can see, and I guess that it goes in a way that what you are asking, like how can you change the MST, because it's an important part of the skater, right? So this kind of shows it that for the MST that is used for the REDCAP, since it's based on the dendrogram and not the Prim's algorithm applied to the similarities of the variables that we have, so it's a different algorithm, it results in a slightly different MST. It's not that much different, and of course we wouldn't want it to be like very different or completely different, because then that would be show like how sensitive the methods are to this. But it's still, we can see some differences, and there's, of course, these differences will reflect in the results. But overall, we got a similar result, right? We still have this very large light blue region. And I'm not sure if I still have the result from the skater. Yes, I do. So we can compare. But from the REDCAP algorithm, the method, we see that it identified like two different regions in the southern portion of Ceará, whereas in Skater, we don't have that. We have just this huge, large light blue area. Okay. So yeah, it's just different MST. So what should we do now? I mean, my suggestion would be, if you end up with a result like this, start again playing with minimum region size or minimum bounds for population, depending again on your applications, to try to get more balanced, a more balanced regionalization. And by being more balanced, it will also tend to be more intuitive and then more easier to interpret. And then once you're happy with the division that you have, with the zoning that you get in the end, then make sure that you're able to label the clusters so you're able to identify exactly why they are different, why these regions are different from each other, right? And for all the approaches, all you have to do is check, again, the cluster centers, and the cluster centers should point you towards the direction of this labeling, right? Should identify to you what are the differences between each of these clusters. Sounds good? Any questions, comments? Okay, so stop this.